Hi, this is Hyeonjun
and Jihyong
from the Korea Advanced Institute of Science and Technology, the first source of XVFI, Extreme Video Frame Interpolation. We've equally contributed to this work, advised by Professor Munchurl. I'll be narrating the first half of this video, and Jihyong will narrate the second half. Recent deep learning-based video frame interpolation networks are often optimized for existing low resolution and low frame rate datasets. The LR-LFR datasets may lead to poor VFI performance for 4K or higher resolution video with larger motion. Thus, we propose a new dataset of 4K 1000 fps videos with an extreme motion to the research community. The below figures show the examples of the dataset. We also propose an extreme VFI network called XPFinet. It had several properties specialized for interpolating high-resolution frames. Even if training is once over, our XVFinet is scale additive to the various spatial resolution. And XVFinet is structurally efficient during inference and estimates optical flow stably. For the proposed dataset, we photographed 4K resolution at 1000 fps with various scenes. Then we build the dataset considering the scene diversity and degree of occlusion and optical flow extracted as shown in the below figure. As shown in the table, our datasets contain comparable occlusion but significantly larger motion compared to the previous VFI datasets. X4K 1000 fps consists of X-test and X-train. X-test contains 15 scenes of 4K resolution to evaluate VFI method. On the other hand, X-train contains about 4,000 clips of cropped patches for the training page. Our datasets are publicly available at GitHub page. This is the XPFinet Framework. It has a shared recursive multi-scale structure that can adapt to spatial resolution and degree of motion of input frames. After the training, XVFinet can start from any downscale input upward from an even smaller scale. At the same time, the second module, BioFT, only operates at the original scale efficiently at inference. And our method achieves state-of-the-art performance on HR datasets with a lightweight structure. This figure shows the architecture at each scale. In BioFI module, bidirectional optical flows between input frames are estimated from recursively downsampled features. The predicted optical flows are provided to the next scale level. And in BioFT module, optical flows from time t to input frames are approximated by CFR, which will be described in the next slide. The approximated optical flows are refined and used to warp the input frames to interpolate the target frame. The warped frames are refined to be the final result at this scale level. As described in the architecture slide, our method is based on the warping operation by optical flow from time t to input frames. This can be obtained by the flow reversal of the optical flows between input frames. However, this causes holes to appear. On the other hand, two bidirectional flows complement each other. Therefore, we propose a novel flow approximation called complementary flow reversal, CFR. Compared to the flow reversal, CFR is helped by the complementary flow, which effectively removes the holes by reducing the possible empty sets and ones. Jihyong will now explain the experimental results.
From now on, Jihyong will narrate the last half. We compare our XVFinet with 3 previous VFI methods whose training codes are publicly available. For a fair comparison, we retrained the previous methods on X-train under their original hyperparameter settings while setting the same total iterations of XVFinet. This table shows quantitative comparisons for multi-frame interpolation on both X-test and Autobit dataset. Our XVFinet with STST set to both 3 and 5 clearly outperforms all the previous methods with large margins on both datasets, even though the number of model parameters of our model is significantly smaller than those of the others. It is also worthwhile to note that our model can operate on 4K frame at once, without any patchwise iteration with the help of the lighter model size. Especially for the X-test, which contains extreme motions in 4K frames, our model can effectively capture large motion in earlier stages. XVFI can also synthesize temporally consistent frames due to CFR to precisely approximate intermediate flows. Center frame interpolation methods such as Adakov, FFlow tend to synthesize intermediate frames generally worse than those of arbitrary time VFI methods such as dyne and hours. The errors of the CFI methods tend to be accumulated iteratively due to inaccurate predictions. Our model can accurately generate intermediate frames at arbitrary time t. This tendency can consistently be inspected in PSNF profiles for multi-frame interpolation on X-tests as shown in this figure. This figure shows a visual comparison on 4K X-test. The first column images show overlap 2 4K input frames. As shown, huge pixel displacements are observed, which is very challenging for VFI. Our model surprisingly captures very complex structures of objects with extremely fast motions, which are failed by all the previous methods. These visual comparisons also show our XPFiNet's superiority on the one of the previous VFI benchmark dataset named Autobi dataset with HD resolution. We compared the 3 flow approximations that enable to produce intermediate frames at arbitrary time t. We approximated ft0 with the 3 methods using the 2 bidirectional optical flows, which are obtained by IRRPWC between the input I0 and I1. The 3 methods are linear combination, flow reverser, and complementary flow reverser, called CFR. This figure visualizes an example of the approximated optical flows by the 3 methods and the pseudo-ground truth which is estimated between IT and I0 by IRRPWC. The linear approximation reveals misalignment due to the different anchor frames. The flow reverser resolves this problem but is inferior to the linear approximation because it causes holes that are not projected from any flow vector. On the other hand, our proposed CFR can appropriately fill in the holes since the bidirectional flows complement each other. The previous visual tendency is also consistently shown in a quantitative evaluation by endpoint error on Vimeo dataset. The average EPEs for the 3 methods are calculated between the approximated flows and the pseudo-ground truths. We also trained 3 VFI models from scratch by adopting each of the 3 flow approximations in their BioFT modules. This comparison also shows the superiority of our proposed CFR for VFI. The lowest scale depth STST for the inference can be adaptive to the degree of motion magnitudes and spatial resolution of the input frames, even after one's train. We show the adjustable scalability of our framework for diverse combination of STRN and STST. As shown in this table, the performance are generally boosted by increasing STST, with the help of effectively enlarging receptive field sizes and elaborately refining the resulting flows. This trend is also observed in this figure. The details of the objects, letters, and textures are more precisely synthesized for STST of 5 than 3 visually. This figure shows the visualization of learned optical flows and occlusion mask of our network. As expected, estimated flows at the upper level seem finer than those at the lower level. The coarse-defined structure gradually helps the whole XPFinet framework boost the finer VFI. On the other hand, the occlusions and flow magnitudes of the Autobi dataset are much smaller than those of X-test. Our model can adaptively show better performance on the Autobi dataset with smaller resolutions than X-test by regulating STST, which also clearly supports the efficacy of our adjustable scalability. To show the robustness of our XPFinet framework for LR-LFR benchmark dataset, we construct a variant called XPFinet V for lower resolution. We compare it with 4 SOTA VFI methods in terms of PSNR, runtime, and motor size. As shown, our XPFinet V outperforms these 3 methods with a significantly smaller model size by taking advantage of the recursive multiscale and shared structure. However, XVFi shows lower performance than those of FatFlow, but has a much smaller model size, only with 5.4% of the number of the FatFlow's parameters, thus leading to about 7 times faster runtime. As a result, our XPFinet also shows its robustness to the ERA-ERA5 benchmark dataset by simply adjusting model scale factor M, strn, and STST. This visual comparison also qualitatively supports our framework's robustness on Vimeo dataset. Following demo videos simultaneously show 4 4K X-test video results. Our 8 times longer results are encoded at 30 fps to be played as slow motion video. The input frames have 4K resolution of 30 fps and are converted to 240 fps by each VFI methods. For the first scene with even extreme back and forth motions of a propeller with zoom out, our XPFinet can surprisingly capture such a complex motion, but the SORAs fail to interpolate the sophisticated tips of the propeller pointed by the yellow arrows. For this scene, the rightmost front car moves very fast, so all the previous methods failed to capture it denoted by the yellow arrow, adding severe artifacts. On the other hand, XPFinet precisely captures the especially right edges of the rightmost car. For the last scene, even while riding a fast-moving car, XPFinet better captures far tiny structures such as electric wires, seen at the left part, and closer pole with a large pixel displacement pointed by the yellow arrows. All relevant codes, including the proposed dataset, are released on GitHub. Please visit us at session 11 for any further discussions. Thank you.